So today we're going to talk about measuring static friction. Excuse me one second. We're going to measure static friction, or more importantly, we're going to measure the coefficient of static friction. Now, coefficients are something that are never derived. We don't have an equation to describe the coefficient of static friction. And usually when we talk about the coefficient of static friction, we're talking about the interaction between two surfaces. So we typically do not have an equation for that. There's just way too much randomness associated with the interaction of two surfaces. I mean, the roughness of a surface is not uniformly rough. So it's very difficult to even imagine coming up with an equation with that. So what we do instead is we come up with a way in which we can measure those coefficients. Okay, so the device that we're going to use for this lab is designed specifically to measure the coefficient of static friction. And all it is it's a plank. It's a plank with a hinge on one side. Okay, so I have a hinge over here so that they get a little bit of it's not scissoring actions, but you can swing this at all sorts of different angles. And then you have a device right here that's designed to measure your angle. Okay? Now that angle is critical to determine the coefficient of friction. So what ends up happening to measure that static friction is we look for the point in which we've reached our maximum static friction. We reach the point where the object is no longer going to stay stationary. It's going to start to slide. And at that point, we stop moving the plank up. So we're moving. The object starts to slide, and we stop right there. We record that angle, and from that angle, we're able to calculate what that coefficient of static friction is going to be. Okay? So we're looking for that point where it's just going to start to slide. Cool? To determine what that coefficient is going to be, we have to do a free body diagram, and we've got to apply Newton's second law to it. First thing we do with a free body diagram, we've drawn my box. All of our arrows are coming out of that box. We only do free body diagrams for one object at a time. So just on that one object, the forces of interaction are, well, we've got gravitational. Okay, we got the force of gravity. We have the force normal, and remember normal is perpendicular to that surface. So this plane right here, that normal force has to be perpendicular to it. And lastly, we have what we look at, the force of friction. Okay, cool? So those are the three forces that are interacting. Now, if I am to continue to lift this block up beyond the point where it just starts to slip, we experience an acceleration. And that acceleration is in this direction. Okay? It's not a force vector, that's why I've dashed it. It's just simply in that direction. That's important because I want to set up my coordinate system to take advantage of that direction of acceleration. If it's going to be accelerating in this direction, I want that direction to be one of my axes. Okay? Cool? So what I'm going to do is I'm going to set my axes like this. Here's my y, and here's my x. Okay? So that's going to be my axes. So my acceleration, if I continue to lift it, would be in the negative x direction. My normal is in the positive y, and my force of friction is in the positive x. Okay? Cool? Now, Newton's second law says, well, if I know all the forces in the x and I know all the forces in the y, I can sum them all up and I can set that equal to ma. Okay? Cool? So the sum of my forces in the y direction. Well, I've got one. I've got one that's really obvious. That's my normal. That's in the positive. My second force is the portion of gravity. I've got a section here of gravity in this direction, and I've got a portion of gravity in this direction. Okay? So this portion of gravity turns out to be mg cosine theta. And this portion of gravity is mg sine theta. If you don't know where they come from, then just go back and view some of those incline problems that I've created as an example. So my normal force is positive. This portion of gravity downward is negative. Negative mg cosine theta. Cool? And we don't expect any acceleration to be in this direction, so this plus this gives me 0. Cool? Now, talking about in the x direction, I've got my force of friction, which is positive. Okay? And then I have this portion of gravity, and that's going to be negative. That's moving down the incline. It's moving in the negative x direction. Now, we are talking about the instant just before it starts to move. So if it's not moving and it's not changing its motion, then we can say that the acceleration is equal to 0. Cool? All right. So I've got my two equations. Okay? I know they're both equal to 0. So what I'm going to do is I'm going to set some of these ideas equal to each other. I'm going to solve for each one of those terms. Okay? So I have normal is equal to mg cosine theta. That 0 is not all that important to me, so I'm going to get rid of it in the equation. How I do that is move this second term over to the other side. Okay? I do the exact same thing for the x direction, and I'm left with the force of friction is equal to mg sine theta. Now remember that this is only true for that instant before it slides. Okay? Cool? All right. So I know the equation for the force of friction is the coefficient times the normal. Okay, so all I did was substitute in the equation for the force of friction, which is the mu, the coefficient, and it's the coefficient of static friction, times the normal, that's the force of friction. That whole thing was equal to mg sine theta. Well, I know that normal is mg cosine theta. Now I'm left with this relationship, which is really cool, because it doesn't matter the mass of the object, which is great, because the coefficient is a discussion of the roughness of two surfaces. It shouldn't have anything to do with the mass. It's only about the roughness of the two surfaces. It also says that the acceleration due to gravity, what planet it's on, that shouldn't make a difference either. We're only talking about the roughness of the two surfaces. The surfaces aren't going to be any less rough or any more rough if we fly to Jupiter. Okay? So those go away, and I'm left with mu static cosine theta is equal to sine theta. I'm going to do one last thing. Mu static is equal to sine theta over cosine theta, which is equal to tan theta. Okay? So, when you lift your device and you get that angle, all you have to do is put the tangent in there. But take the tangent of that angle and you're able to calculate the mu static. What I want you to do for this lab, though, is every time you've determined the coefficient of static friction between those two surfaces, I want you to go online and I want you to find the measured value, the accepted value by most of the industry, and see how your value compares to the other one. Give me the percent difference, okay? And I want you to do that for 5 different types of objects. Do your wander around the room. You know, I've got plastics, I've got woods, I've got irons, I've got copper, I've got wood, I've got all sorts of junk. What I want you to do is I want you to find 5 items and try all 5 items. and determine what the coefficient of static friction is for each of those items. Then compare with the literature value. See what they say online. What do you expect static friction of wood on plastic to be? Okay? Cool? That is the static friction lab.